Hello. What we're going to do now is review minerals. So let me just share my screen. Okay, so on the left, I've got a list of the main topics we're going to cover during this presentation. One of the big deals about how to teach minerals is finding a way to engage one's students. One approach I've used is looking at the minerals used to make a cell phone. There's lots of resources out there on this. Quite a few of the minerals that supply the elements, and we'll be going into this, that are used to make a cell phone are somewhat obscure. So it depends on the students that you're working with. So let's just move along here. So first of all, I want you to just step back a moment. If someone says the word mineral to you, what comes to mind? What do you connect it to? So just pause, take a moment, and, make a list. If you already know minerals, make a list that you think your students might make. What would they say if they would think about if the word mineral was used? Okay, so what we're looking at here is a bunch of bullet points, and these are words that or ideas that people typically come up with. So at the top somewhere is usually, oh, vitamins and minerals. Well, this is a huge misnomer. When people talk about vitamins and minerals, when they're using the word minerals there, they're actually talking about elements. So, well, this I think was from some potato chips, I'm not sure. But here in this red circle, we have our vitamins and minerals. But here, calcium, iron, and potassium, those are the elements, but they get called minerals in nutrition. Go figure. People often think they're precious. A lot of minerals have minimal value. They may or may not be precious. A lot of people think of jewelry. Yes, jewelry uses minerals and rocks. A lot of people assume that they need to be glittery or shiny. Well, sometimes. Depends on the nature of the mineral. It may also depend on how that mineral has been cut to go, if it's in jewelry. Is it valuable? That's kind of the same as precious. It may or may not be valuable. It depends on its potential for being used and what it might be used for. Comes from the earth. Yes, all minerals come from the earth. Makes up rocks. Yes, minerals make up rocks. And then the last one here, mineral water. Well, this again is kind of weird. Mineral water is kind of a complicated thing. It's water, and nearly all water, unless it's been distilled, has lots of elements or ions of elements in it. And there are actually rules about what constitutes mineral water, what constitutes spring water. So minerals, mineral water doesn't have chunks of minerals in it. It has different elements that are floating around in with the hydrogen and oxygen. So that's a review of that little thought. So moving on from that, what are the criteria for being a mineral? Well, there are 5 of them listed here. The first 3, it must occur naturally, it must be solid, and it must be inorganic. In other words, not living. They're pretty straightforward. The next 2 in red are more complicated. We're going to come back to them in a moment. Here, I just put in a image of, well, this is kind of dramatized, most deadly minerals. So you'll notice that galena, the one that I identified in your rock and mineral kit that has the warning in it, yeah, that's on this list, and that's because it includes lead, the symbol PB in its structure, and lead in any ingested in any amount is toxic. So let's move on now to just think about how minerals form and their context. So, what's important is the relationship, if we start on the left, between atoms, elements, minerals, and rocks. So, we're going to move backwards now. If we have rocks at the Earth's surface, those rocks are made up of minerals. And depending on how those minerals form, where they form, etc., you end up with different rocks. So if you look over on the right, what you'll see is, in this case, 2 igneous rocks, but the distinct different colors in those rocks are the different minerals that make them up. So that's why it's useful to be able to identify the minerals. Then we can use the percentage of the different minerals and their shapes and their organization to name the rocks. Well, let's move back to elements now. Minerals are made up of varying proportions of different elements. And then the smallest possible subdivision of an element that still retains its essential properties is a single atom of that element. We're going to dive a little bit deeper here. So remember that elements are on the periodic table. They all have a symbol, which is either 1 capitalized letter or 2 letters, the first being capitalized and the second being lowercase. And we're not going to spend a lot of time thinking or delving into the periodic table. There's plenty of opportunity for you to do that with your students if you want to, but let's just look at the information that's in each of these boxes. Every element has an atomic number. That's the number of protons or electrons in it. And it also has an atomic mass. That's the mass of the protons and neutrons that make it up. So, thinking now about atoms. Here we're looking at some information about 2 of the most important elements in earth science. That's oxygen and silicon. And that's because these are the elements that are most abundant in Earth's crust, and they join up to help make the silicate minerals. Now, we're going to go back to that definition, and we're not actually going to do it in order. I'm going to go down to that bottom part of the mineral definition. It says it must have a definite chemical composition that varies between specified limits. Okay, what does that mean? It means that you have to be able to write out a chemical formula for the mineral. So, for example, the mineral halite has Na, sodium, Cl, chlorine in it. And they are present in equal amounts. We can tell that because there is just Na and Cl. That's halite, commonly known as salt. And so that's the sort of the proportion of the two. Now, what does the between specified limits mean? Well, this is where if we have a mineral, like in the case of the little tiny green crystals here of the mineral olivine, it has a kind of funky formula. Notice the Mg for magnesium and Fe for iron here. They are in parentheses. And what that means is, well, it could all be magnesium. It could all be iron. But there's some amount of magnesium and iron. And overall, the proportion of them to SiO4, one of them, the main building block part, is there's two of them for every one of the SiO4s. So that's this specified limits business. All right. Now, we're back here. We've looked at the definite chemical composition. That's our formula. Now we're going back up here. It must possess an orderly internal structure. Its elements, and obviously the atoms of those elements, therefore, must be arranged in a definite pattern. So, if we go back to thinking about our halite, it's made up of sodium and chloride. And the way those atoms are, or ions, because they have charges, are organized is absolutely predictable. This is like packing things in a box. How are they packed together? And every mineral has to have a predictable structure, and that's the way it's packed together. And the way it's packed together ends up controlling the shape. So if it grows to form a perfect crystal, and lots of minerals don't do this, that's why it can be very hard. We don't typically see beautiful, perfect crystals. But what we've got here in the image I'm pointing to right now is some perfect cubes of halite. If you use your magnifier and look at some kosher salt, just put some in the palm of your hand, you will see that it's made up of lots of little cubes that look not unlike this. So this cube shape is essentially what we call the crystal form of a mineral. Now, let's take another step back. We've got the basic definition taken care of. Why is there such a variety of minerals? So let's just look at the elements that dominate in Earth's crust, the upper 5 to 75 kilometers or so of Earth. And what I hope jumps out at you is, oh my goodness, she was right. Oxygen and silicon are the dominant elements there. So the silicate minerals, that's the minerals that are made up of oxygen and silicon as their basic building blocks, are the most dominant mineral class. Now, there are a bunch of other minerals or mineral classes. So if people talk about oxides, they mean minerals that have some other element, for example, iron joining with oxygen. There wouldn't be silicon here. Or carbonates. I forgot to put Ca. Okay, the carbonates have calcium and carbon and oxygen. There's the halides. Oh, that's what our halite was. It was sodium chloride. So there's a bunch of minerals that are part of the halide class. Sulfides are the ones that have S or sulfur. So think about iron sulfide. Sulfates have SO4 as their building block. And then there are the minerals that are just made up of one element. Examples of that would be gold, silver, or pure copper. And I think you already know that the most abundant class is the silicate minerals. And that's because of the abundance of oxygen and silicon in the crust. Now, how are the silicates actually built? So this is the key building block for silicate minerals. There's one, that's the blue thing here, silicon atom in the center, and it's surrounded by 4 oxygens, and they're sharing electrons. And this structure is called the silicate tetrahedra, and it is the building block for all silicate minerals. The way these tetrahedra are joined together or sandwiched together by other elements is what basically controls which silicate mineral group we're looking at. Now, a little bit of a heads up, there are 4 different S words to wrap your brain around, and it can be easy to misuse these. Silicone, this is a resin rubber-like substance, typically synthesized from hydrocarbons. Not always, but so that's what you do when your grout starts falling out. You probably use some silicone. And it's also, there is also silicone oil material. Silicon is the element Si on the periodic table, what we've been talking about. Then silicate, we were just talking about the silicate tetrahedra. So that refers to the silicate tetrahedra. Or people use the word silicate for the entire class of minerals that use the silicate tetrahedra as their building block. And then finally, silica, and that's the common term for the mineral quartz, which has the formula SiO2. So that's our S words. Now, how does this silicate tetrahedra thing work? So essentially, the atoms of the elements either have a positive or negative charge of some kind. And, you know, that gets more into the chemistry side of things. You could spend a lot of time on this. The short story is those elements want to join up with other atoms to make sort of happy neutral compounds. And the word compound is just word for elements that are joined together. So here we have a bunch of atoms. The main negative one is oxygen, and it's just looking to become happy and neutral by joining up with something that has a positive charge. And they do that in a bunch of ways. Now, the different silicate mineral structures. So remember, we've got this silicate tetrahedra. Then it's all about how those tetrahedra get packed together. And the way they get packed together, obviously that affects the terminology we use, but that's because the way they get packed influences their essential properties, how they break, how many layers or cleavages they have. So if you have just single tetrahedra, like the mineral olivine, you've just got individual tetrahedra that are all joined together. But once it gets really interesting, once you start having chains, there's these different chains of tetrahedra, and they share other elements in different ways, single chains, double chains, and you'll see that certain mineral groups are associated with different silicate structure, or I've been using the word packing here. The micas, muscovite and biotite, those are the ones that are very platy, flat-like, that you can kind of flake, separate with a fingernail. They make sheets. Those sheets are sandwiched together, and those are the sandwiching elements are actually weak bonds, and that's why you can pull it apart. Then there's feldspars and quartz. So, and here I've just got some enlarged images if you want to interrogate them later, and these slides will be in D2L. Here, this just pie diagram gives you a sense of the relative proportion of different mineral classes in Earth's crust. So look here, only 8% of minerals are non-silicates. That means 92% of all minerals are some kind of silicate. They are built using the silicate tetrahedra, and they show all the different ones here. Next up, let's think about how we identify minerals. And we've got 7 approaches to helping us identify minerals right here. We've got 2 street plates. In this case, there's also a black one shown, a copper penny, a magnifier, a steel wire, a magnet, and this is supposed to be a dilute hydrochloric acid bottle. This is the top for it that goes on there. I'll talk about that a little bit further on. So let's take a look at what we do to identify minerals. So first of all, there's the hardness of the mineral. So a character called Mo developed this scale, goes from 1 to 10, with 1 being the softest and 10 being the hardest. And there's actually a mineral that's identified for each number on the scale. So the mineral talc has a hardness of 1. And then you go up to diamond, which has a hardness of 10. Now, the really fun thing is we use a whole bunch of common everyday objects to try and figure out how hard a mineral is. Fingernails are 2.5 in hardness, and that applies to natural fingernails and fake fingernails. So if you can scratch something with your fingernail, you know that that mineral is softer than 2.5. So it could be gypsum or talc, for example. A copper penny has a hardness of 3.5. So if you can scratch something with it, that mineral is softer than 3.5. That's useful for the mineral calcite, for example. Now, it gets a little bit complicated once one starts getting into metals, because the way different metals are made, they have slightly different hardnesses. So that accounts for some of the discrepancies in the hardness here. A glass plate is, and when we say glass plate, I don't mean like a table plate. I mean just a sheet of or piece of glass, even from a broken window, will have a hardness of 5.5. Most like Swiss Army knives have a blade, and that should have a hardness of about 5.5. Once you start getting into other nails, it gets really complicated. The masonry drill bits are a lot harder. Are they always 8.5? My experience says no. Steel nails, 5.5 to 6.5. There's one thing that isn't shown over here, and that's the little porcelain tile that you have. That has a hardness of 6.5. So if you take a mineral, drag it across the streak plate, and it leaves a streak, a line of color, that means that the mineral is softer than 6.5 because the streak plate pulverizes it. Next up is a concept called luster, and it gets defined as the appearance or quality of the light that is reflected from the mineral surface. So the easiest division is, okay, it's either metallic or non-metallic. And if it's metallic, that means it looks like metal, you know, sort of chrome, brass, silver, gold. On the other hand, if it's non-metallic, we use a bunch of goofy words for it. And you'll see these in tables that are supposed to help you identify minerals. Vitreous means glassy. Pearly looks like pearls. Resinous is that kind of in-between reflective nature of something that's resin. There's a little bit of light that seems to bounce off it, but it's slightly earthy or dull. There are a lot of minerals that will, if you look up their luster, they will tell you that it ranges from vitreous to earthy or dull. And you may just throw up your hands at that. But look at the sample here on the lower right. Here, they're on these flat surfaces, they're actually cleavage surfaces. It will be vitreous or glassy, light will reflect off it. But on this almost cute, square-like end, it's very dull. It doesn't reflect the light well. This would be earthy or dull. So that's why you get these goofy definitions. Galena would count as metallic. It's a silvery gray. Okay, so next up, color. Now, I want to give you a heads up here. Color can be useful, but also beware, because small amounts of impurities can change the color dramatically. So if you look at all 4 of the samples here, they're all different types of quartz. Basically, the formula SiO2, that's the formula quartz has once all those silicate tetrahedra are packed together. And because of the proportions of silicon and oxygen, the formula ends up being SiO2. Anyway, these are all different types of quartz. You may recognize the pinkish purple one here as amethyst. And over here we've got, I think, some citrine. This would be in the bottom right, smoky quartz. And then plain old ordinary quartz in the upper left. And they just different colors because different impurities, in other words, different elements or atoms of those elements have snuck into the structure as those crystals were growing. So number 4 is called streak. And I've already mentioned the streak plate. This is what's here, this porcelain tile. And if you take your mineral sample and you drag it across the streak plate and it gets powdered, leaving this ground up mineral dust, the color of the streak can be diagnostic. And as you know, it also tells you about hardness. Here we're looking at 2 varieties of the mineral hematite or hematite. Pronounce it both ways. Can call it 2 different presentations. One is a silvery gray and the other is a reddish brown, but they both give a reddish brown streak. Now, number 5, I've kind of hinted at this already. cleavage. So remember that we talked about how those silicate tetrahedra get packed together in different ways, whether it's chains, etc., etc. The word cleavage refers to a plane or flat surface along which a mineral breaks. And we can use the number of cleavages and the angles at which they intersect to identify minerals. Some are easier than others. So if you have one cleavage, the really good examples are the mica minerals, where you have just those plates or layers. It's the one that looks like a book with pages you can peel off. Then here there's 2 at 90 degrees and so on. So the number and kind of cleavage that develops is a consequence of how those building blocks are, in other words, the silicate tetrahedra, are packaged together. So often, if you hit a sample and it breaks, it will break along those cleavage planes. If you, on the other hand, have a sample that's defined by the crystal shape, you don't want to hit it with a hammer, because you'll destroy that nice crystal form, and it may or may not have cleavages that show up when it breaks into little bits. The cleavages influence how a sample breaks or fractures. Okay, so I've already mentioned crystal form. So let's just think about how the word crystal gets used. So when a mineral grows unimpeded, in other words, not pushed against by other minerals, it will form perfect crystals. And we call this growing in open space. On the right here, we've got some amazing gypsum crystals that grew in a mine in Mexico. And they discovered these sometime in the past 10 years, but they grew from a solution. So this is how one way that different minerals grow. They effectively either grow from molten material, magma. They will form the elements all joined together and they grow crystals. Or they grow from some kind of watery solution, and that's what happened here. There was these hot brines that were rich in the right elements, and they then formed these crystals. Minerals can also grow to form very nice crystals in a rock when it's heated up or metamorphosed. The elements just, it's like a square dance. The elements just move around and join up in a way that is appropriate for the right temperatures and pressures. So one thing to remember is that even if a sample doesn't outwardly look like your vision of a perfect crystal, it will actually have some kind of crystal form, even though that may not be obvious to you. And I want to just remind you here too that if you've got a mineral sample, the shape may not be that of a crystal. It may be, the shape may be controlled by the way it's broken up or cleavage. And then there are what I call the other criteria. The big one is the HCl test, and it uses dilute hydrochloric acid, 5% HCl, and you just drop a little bit onto a rock that contains carbonate, calcium carbonate, and you will see evidence of a chemical reaction. What is that? It gives off a gas and it leaves a residue. So effectively it fizzes. Sometimes you have to look at where you've dropped the acid with a magnifier. Now, all the textbooks you see say, oh, you can use household vinegar. Well, I quite honestly, have never had good results from household vinegar. I've always had access to dilute HCl. One thing that you can do is get muriatic acid from a hardware store, but you have to dilute that. You can't use it in concentrated form. So this is a case of, if you want to look at this, check with your safety person and read the fine print very carefully. Magnetic or not. One thing to remember if you're checking to see if a sample's magnetic is it's much easier to put the magnet on the table and move the sample towards the magnet and see if the sample picks up the magnet. If you're holding a magnet in your hand, it's sometimes hard to tell whether your hand's moving the magnet or whether it really is being pulled towards the sample. And then one can also use density to help evaluate the identity of a sample. So with that, with that, I am going to stop sharing. One thing I want to remind you now is if you have kids coming into class, or you go out and are poking around maybe on a riverbank, a lot of times you'll find stuff and you'll just look at it and go, oh my goodness, what is this? Kids will often bring in what I call grubby pocket rocks or grubby pocket bits, and they want to know what it is. And this is something that happens a lot. I internally roll my eyes because half the time it isn't really obvious. And I end up asking lots of questions about where they collected it. And I'm often able to figure out what it is using all these tests and using what I know about the geology and what is most likely to be in a particular stream. But it can be really hard to identify those grubby pocket rocks. So enjoy learning about minerals. We're going to stop here. It's been good.